Welcome back to WeldFabWorld, your go-to source for everything welding, fabrication, and quality control. Today, we're diving deep into one of the most critical inspection techniques in the welding industry, hardness testing. Whether you're a certified welder, a QC inspector, or an engineering student, understanding hardness testing is essential, because it directly tells you if a weld is strong, safe, and fit for service. By the end of this video, you'll know exactly what hardness testing is, why it matters, the main testing methods, how to read the numbers, and the key challenges engineers face in the field. Let's get into it. So what exactly is hardness testing? At its core, hardness testing measures a material's resistance to permanent indentation. A specially shaped indenter is pressed into the surface of the material under a known load. The size or depth of the indent left behind is measured, and that gives us the hardness number. In welding, we don't just test one spot. We test three critical zones. The weld metal. This is the filler material that solidified during welding. The heat-affected zone, or HAZ. The area of base metal that was altered by the heat but did not melt. The base metal, the original unaffected material, which serves as our hardness reference point. Each zone behaves differently because each went through a different thermal cycle during welding. And hardness tells us whether that thermal experience left the metal in an acceptable condition, or in a potentially dangerous one. Think of hardness testing as a health check for your weld. Just like a doctor checks your blood pressure to assess cardiovascular health, we use hardness numbers to assess the metallurgical health of a weld joint. Let's talk about why hardness testing is not optional, it's a necessity. Here are 6 critical reasons. Reason 1. Quality verification. Every major welding standard, ASME, AWS, ISO, specifies hardness limits. Hardness testing confirms that your weld meets those requirements. Without it, you're just guessing. Reason 2. Detection of brittle zones. When a weld cools too quickly, or when the wrong filler metal is used, the HAZ can become extremely hard and brittle. Brittle zones are crack magnets, especially under cyclic or dynamic loads. Hardness testing catches these dangerous zones before they cause catastrophic failures. Reason 3. Soft spot identification. On the opposite end, overly soft zones can form when heat input is too high, causing grain growth and loss of strength. These soft spots can deform or fail prematurely under load. Hardness testing identifies them early. Reason 4. WPS and PQR qualification. Before a welding procedure is approved for production use, it must be qualified. Hardness testing is a key part of the welding procedure specification and procedure qualification record process, ensuring that the procedure consistently produces acceptable welds. Reason 5. Verifying post-weld heat treatment, PWHT. Many high-strength or alloy steel welds require post-weld heat treatment to reduce residual stresses and soften the HAZ. Hardness testing before and after PWHT confirms whether the heat treatment was effective. If the hardness didn't drop as expected, the PWHT failed. Reason 6. Service life prediction. Hardness data helps engineers predict how a weld will behave over its service life, under pressure, temperature, corrosion, and mechanical loads. This is especially critical in industries like oil and gas, power generation, and aerospace. Let's look more closely at the 4 main areas where hardness measurements are taken during a weld inspection. 1. Weld metal, WM. This evaluates the filler metal properties and how well fusion was achieved. The weld metal should have adequate hardness for load bearing, not too soft, not too hard. 2. Heat affected zone, HAZ. The HAZ is the most critical and sensitive zone. It experienced rapid heating and cooling without melting, which can cause microstructural transformations like martensite formation in steels. The HAZ is often where hardness is highest and cracks are most likely to initiate. 3. Base metal, BM. The base metal serves as the baseline reference. It tells us the original hardness before welding affected it, and allows us to quantify exactly how much the welding process changed the material properties. 4. Transition zones. The gradients between the weld metal, HAZ, and base metal are also important. Steep hardness transitions can create stress concentration points. A smooth gradient is generally a sign of a healthy weld. Now let's get into the actual testing methods. There are 4 primary methods used in welding inspection, and each has its own strengths depending on the application. Method 1. Vickers Hardness Test, HV. The Vickers test uses a square-based diamond pyramid indenter with a 136-degree face angle. The indenter is pressed into the surface, and the diagonals of the resulting square impression are measured under a microscope. The Vickers hardness number is calculated from the applied load divided by the surface area of the indentation. Key characteristics: high precision, can measure very small areas. Ideal for HAZ testing, where the zone can be just 1 to 2 mm wide. Works on a continuous scale from soft to very hard materials. Standard for most welding procedure qualifications per HAZ D1.1 and ISO standards. Can be used for micro-hardness testing, loads as low as 1 gram force. Typical hardness limits for carbon steel welds: less than 350 HV for non-sour service, and as low as 250 HV for sour service environments per NACE MRO 175. Method 2. Rockwell Hardness Test, HR. The Rockwell test measures the depth of penetration of an indenter under a major load compared to the penetration made by a preload. It uses either a diamond cone, called a Brinell indenter, or hardened steel balls depending on the scale. Key characteristics: fast and simple, results are read directly from the machine dial. No microscope needed. Multiple scales available: HRC for hard materials, HRB for softer materials. Widely used in production and shop floor quality control. Less suitable for narrow HAZ regions due to larger indentation size. If you're doing rapid production checks on finished weld components and need a quick no-go reading, Rockwell is your best friend. Method 3. Brinell Hardness Test, HB. The Brinell test uses a hardened steel or carbide ball pressed into the surface under a heavy load. The diameter of the resulting circular impression is measured, and the Brinell hardness number is calculated. Key characteristics: best suited for coarse-grained materials like castings and forgings. Larger indentation area averages out microstructural variations. Commonly used on base materials before welding. Not suitable for narrow zones like the HAZ, impression is too large. Referenced in ASTM E10. Method 4. Portable hardness testers. When the work is in the field, on a pipeline, pressure vessel, or structural component, you can't bring the material to the lab. That's where portable hardness testers come in. Common portable methods include Lieb rebound hardness, used in most handheld units, UCI, ultrasonic contact impedance, suitable for thin sections. Portable Vickers, Rockwell attachments. Key characteristics: essential for in-service inspection and maintenance. Can test in any orientation, vertical, overhead, horizontal. Results can be converted to HV, HB, HRC scales. Accuracy is lower than lab methods. Results should be treated as indicative. Applicable standards and codes. Hardness testing in welds is governed by a comprehensive set of international standards. Knowing which standard applies to your application is critical for compliance. ASTM standards, USA, ASTM E384, microindentation hardness testing. Vickers and Knoop. ASTM E92, Vickers hardness of metallic materials. ASTM E18, Rockwell hardness testing. ASTM E10, Brinell hardness testing. ISO standards, International, ISO 6507, Vickers hardness test. ISO 6506, Brinell hardness test. ISO 6508, Rockwell hardness test. Welding and industry codes. HAZ D1.1, Structural Welding Code, includes hardness requirements for WPS qualification. ASME Section X, Welding and Brazing qualifications with hardness acceptance criteria. NACE MRO 175, ISO 15156. Hardness limits for sour service, hydrogen sulfide environments, typically 250 HV maximum in the HAZ. Always check your project specification to determine which standard applies. The acceptable hardness range can vary significantly depending on the code, material grade, and service environment. Interpreting hardness results. Getting the hardness number is only half the job. Knowing how to interpret it is what separates a good QC inspector from a grade 1. Too high, e.g., greater than 350 HV for carbon steel, excessive hardness, especially in the HAZ, indicates a martensitic microstructure formed by rapid cooling. This makes the zone brittle and highly susceptible to hydrogen-induced cracking, particularly in high-strength or alloy steels. Immediate review of the welding procedure and possible PWHT is required. Hardness too low. Low hardness means reduced strength and load carrying capacity. This can result from excessive heat input causing grain coarsening, dilution effects from filler metal, or an inadequate welding procedure. Low hardness zones can deform plastically before reaching design load limits. Within acceptable range. The acceptable range is defined by your material specification, applicable code, and service conditions. A weld within range means the metallurgy is sound, the procedure is working, and the joint is fit for service. Hardness trends and profiles. Don't just look at individual readings. Look at the trend across the entire traverse. A sharp peak in the HAZ followed by a sudden drop into the weld metal might indicate inconsistent heat input or microstructural gradients that need further investigation. Key challenges in hardness testing of welds. Like any inspection method, hardness testing has its challenges. Let's talk about the 4 most common ones you'll encounter in the real world. Challenge 1. Testing in the narrow HAZ. The heat-affected zone can be as narrow as 1 to 2 mm in some applications. Getting accurate, representative readings in such a tight space requires micro-Vickers testing with careful indenter placement. Missing the HAZ entirely gives you a false pass. Challenge 2. Variation due to welding parameters. Hardness is extremely sensitive to heat input, travel speed, preheat temperature, and interpass temperature. A change in any one of these variables can shift your hardness profile significantly. This is why hardness testing must be done at multiple locations across the weld. Challenge 3. Indenter alignment and operator skill. Proper surface preparation, perpendicular indenter alignment, and smooth load application are all critical for repeatable results. In micro-hardness testing, even slight surface tilt can cause significant measurement error. Operator training and calibrated equipment are non-negotiable. Challenge 4. Dissimilar materials and weld overlays. When testing welds between dissimilar metals, or weld overlays and cladding, interpreting results becomes complex. Each material has different base hardness values and responds differently to welding. Comparing readings to a single acceptance criterion may not be appropriate, you need material-specific limits. Practical tips for accurate hardness testing. Before we wrap up, here are some practical tips to ensure accurate and reliable hardness test results. Always prepare the test surface properly, grind and polish to at least 400 grit for Vickers testing. Use calibrated and certified test equipment. Verify with reference hardness blocks before testing. Place indentations at specified intervals per the applicable standard. Minimum spacing is typically 3 times the diagonal length. Perform a full hardness traverse. Base metal right pointing arrow has right pointing arrow, weld metal right pointing arrow has right pointing arrow, base metal. Document all readings, load applied, scale used, and calibration records. When in doubt, consult the applicable code or a materials engineer. Alright, let's bring it all together. Hardness testing is one of the most powerful tools in a welding quality control program. It tells you whether your weld metal, HAZ, and base material are in acceptable condition, metallurgically and mechanically. The 4 main methods, Vickers, Rockwell, Brinell, and portable testers, each have their place depending on the application, location, and precision required. And whether you're qualifying a welding procedure, performing PWHT verification, or doing on-site maintenance inspection, understanding how to measure and interpret hardness is a skill that will make you a more capable and confident welding professional. For more technical resources, articles, welding standards breakdowns, and inspection guides, visit us at WeldFabWorld.com. If you found this video helpful, smash that like button, subscribe to the channel, and drop a comment below. Let us know what welding topic you want us to cover next. Until next time, keep welding right, keep testing smart, and stay safe out there. This is WeldFabWorld.